Okay, so the next thing that we're going to do is going in the opposite direction. So given an angle theta, what we're going to do now is think a little bit about the coordinates of the point. So given an angle theta, find the coordinates of the point P, and we'll denote those coordinates with x and y. And so there's a couple of easy cases that we can do first. And that you can more or less read off from the unit circle. So the first one that we'll look at is the angle pi over 2. So here if we say theta is pi over 2, then the point that corresponds with that is this point right here, and let me label my axes x and y. So then this point right here has coordinates 0 for x and 1 for y. So let's do another one. Let's look, for instance, at theta equal to 3 times pi. So 3 times pi, that's going around the circle once, that's twice, 2 pi, and then one more time, that's pi. So here we have 3 pi. And the point that corresponds to that is p negative 1, 0. There's a few more that you can do. So for instance, I'll let you do theta is minus pi over 2, and you should find that similar to that one over there, the point is 0 minus 1. So those are the easy cases. Let's do a couple more tricky ones. So complex case 1, it's not that complex, but it's a little bit more work, is what is the point corresponding to the angle pi over 4? So if we take our trigonometric circle, or unit circle, this is the angle theta pi over 4, the point P, x and y. We have to use a little bit of geometry now to figure out what the coordinates of x and y are. And the thing that will yield us the answer here is the realization. We have pi over 4 here. This entire angle is pi over 2, so that's half. And this radius here basically separates the quadrant into 2 equal parts. So what that means is, if we look at this line on which the point P lies, that this is the first bisector. So this is all the points for which x is equal to y. Now we can exploit that in order to find the coordinates of x and y. So let's write down what we know about the point P. We have that, first of all, x squared plus y squared is equal to 1. That's always true. That's the unit circle. And now, secondly, we're going to use the fact that y is equal to x. X squared plus x squared is equal to 1. So here we use that x is equal to y. Now we simplify that a little bit. We get 2x squared is 1, or x is equal to plus or minus 1 over square root of 2, which is plus or minus square root of 2 divided by 2. So here we see a priori we have 2 solutions, the positive and the negative one, but we have to choose the positive one because we know that our point P right here is in the first quadrant. So therefore, we have that P has coordinates square root of 2 divided by 2, that's x, and y is equal to x, so that's another square root of 2 divided by 2. Let's do another one, similar, so case 2, theta equal to pi over 6. And that's also going to require a little bit of trigonometric insight. So if we go back to the unit circle, here's our point P. We draw the radius. This is the origin. And this angle right here is pi over 6. So now let's draw the angle minus pi over 6. So this is minus pi over 6. And let's call this P prime. And now let's look a little bit at the triangle that we form by connecting P, P prime, and O. And I'm going to lift that triangle out and put it on its own here so that we can have a look. Okay. Not very nice, but you get the picture. So this is point O, this is P prime. So what do we know about this triangle? So first of all, we know that this side has length 1, this side has length 1 as well, 1 and 1, and this entire angle right here is pi over 6 plus another pi over 6, so this right here is pi over 3. So I can transfer that here, and we have pi over 3 here. And now, it takes a little bit of looking at the unit circle, and my figure, since it's hand-drawn, is not so great, but you can convince yourself that this is actually an equilateral triangle. So, 3 same sides, 3 same angles. And why is it an equilateral triangle? Well, if you look back at the unit circle here, what you can basically do is you can take this top triangle, this subtriangle, and reflect it across the x-axis and get this lower triangle right here. So in particular, this angle has to be equal to that angle, and therefore they both have to be pi over 3. So we bring that here and here as well. So 3 same angles means 3 same sides, equilateral triangle, and that tells us that the distance between P and P prime is also 1. So if I squeeze that in here, we get that this right here is 1. And then again, because of symmetry, we can tell that these two lengths here have to be the same, and they're each equal to 1 over 2. So now knowing that this length here between P and the x-axis, that's 1/2, that's great, because that tells us right away what the y value for P is. So here we have y equal to 1/2. And here, by the way, it won't really matter, but y equal to minus 1/2. So the fact that we have that equilateral triangle tells us that y is equal to 1 over 2. And so now we have to determine what the x coordinate is. And for that we use the fact that x squared plus y squared is equal to 1. We plug in value for y, doesn't belong there. You simplify that a little bit and you get 3/4 here, and x is plus or minus square root of 3 divided by 2. Again, we have two solutions when we look at the algebra, but only one is going to survive. So again, two solutions, so plus and minus, but we have to take positive solution since P is in quadrant 1. And therefore, we have that P has coordinates square root of 3 divided by 2, 1/2. So that takes a little bit more work, but once you have that, you know the value for pi over 6. So there's a couple of important angles. I'm not going to derive all of them. I'll just draw up the table here, and I'll let it. I'll give it to you to derive the ones that we haven't seen in class. It's a useful exercise to do that, and you'll see these values will come back over and over again. So I would recommend, if you don't memorize them, then at least make sure you recognize them, because knowing them at heart and being able to quickly plug them into formulas is going to save you a lot of time. So for theta equal to 0 radians, we've already seen that x is 1 and y is 0. So let me just draw the trigonometric circle here to make sure that we have everything lined up correctly. So we're given theta and we want to find x and y. So theta 0 is 1 and 0. Pi over 6, we just did have square root of 3 divided by 2 and 1/2. Pi over 4, we also did square root 2 over 2, square root 2 over 2. Pi over 3, we didn't do that one, but if you do the calculation by yourself, you'll find that this is 1/2 and square root of 3 over 2. So I would recommend that you check this. And then last, pi over 2, that was one of the easy ones. So you have x is 0 and y is 1. And we can just add one more. For instance, pi also uses a value x is minus 1, 0. So we've done a couple of examples, some easy ones and some complex ones where we had to look at a geometry argument. For some of the other angles, don't have to start from first principles. You can use what you already know and try to use some kind of symmetry argument. So in order to show how this works, let's do an example. Let's say we're given theta is minus pi over 3, and we want to find the points, and in particular its coordinates, x and y. So if I draw that, then this could be my angle minus pi over 3, and this is my point P. And so I know nothing about minus pi over 3 at this point, but what I do know is theta is plus pi over 3. Just determine that and figure out that that was 1 divided by 2 for the x and square root of 3 divided by 2 for the y. So let's look at that point. So if I take the angle pi over 3 here, and I call this point P prime, then I know that that point has coordinates 1/2 square root of 3 divided by 2. And the crucial property to observe here, and this is also a bit clear from the way that I drew it, is that you can get P, or you can get P prime rather, from the point P by reflection across the x-axis. So a little bit hard to show on the video, but if I take my unit circle and I rotate it 180 degrees over the x-axis, then P turns into P prime and vice versa. So here what we use is the reflection across the x-axis. And what does that give us? Well, if you look at the figure, then you notice that both points, P and P prime, share the same x value, 1/2, and they have opposite y values. So here we have square root of 3 divided by 2, and here we have negative square root of 3 divided by 2. So we get 1/2 for the x value, and the y value for P is minus square root of 3 divided by 2. So in other words, the point P has coordinates 1/2, negative square root of 3 divided by 2. We will see a trigonometric formula in a minute that will let you derive this without having to draw the unit circle, but just to play with this a little bit. So let's do a couple more. Some of them require a little bit more fiddling with the unit circle. So let's start, for instance, with theta is equal to 7 pi divided by 6. And this is quite a complicated angle already. But what you can do is you can observe that this is equal to pi plus pi over 6. And this is good because I know this. I already know something about pi over 6. So if we draw pi over 6, that's probably something like this. And then in order to get 7 pi over 6, what I have to do is add another pi to that. So I have to extend this line to the other quadrant and add pi. So I hope it's clear here. So from this radius to this radius, that's precisely pi. We add pi over 6 here, and we get that this, let me actually put it in a slightly different color. This entire angle here is 7 pi over 6. So now let's again use what we already know. So the point here, P, we have the coordinates of that. We have square root of 3 over 2, 1/2. That we already know. And now what we basically see is that the point, let's be consistent, this is P prime, and this is P, this is the point that we want to find. So here what we use is the property of reflection across the origin. And what that does is it turns x into negative x and y into negative y. So you can, if you can think that far, you can justify this with triangles. But basically here for the point P, what we then get is that the x value becomes minus the x value of P prime, and the y value becomes minus. I draw plus and minus this. Maybe it's a little bit more clear. This length here is minus this length here, and same thing on the y-axis. To do one more, just one more. So I'm also going to put this in a give that some emphasis. So the last one that I want to do here is theta is 3 pi over 4. Again, not an angle that we know a lot about at this point, but you can observe that that's, if you look at it for a bit, that that's pi minus pi over 4. And again, pi over 4, that's something that we should know and love. That's something that we just calculated. So let's start by drawing pi over 4. And then 3 pi over 4, what we basically have to do is we have to take pi and we have to subtract pi over 4. And if you think about that for a little bit, or if you just do it from first principles, what you see is that when you actually erase that little circle that I just drew, you get that this right here is 3 pi 4. So here, what we're going to use is, if we look at, so first finished drawing, this is the point P, this is the point P prime. Here we know that coordinates are square root of 2 over 2, square root of 2 over 2. And what we can see is that if you take the whole unit circle and you rotate it 180 degrees along the y-axis, P turns into P prime and vice versa. So here what we're going to do is use reflection across the y-axis. And in particular, what that then does is it turns my x into minus x, and my y stays the same. So in particular, for the point P, what we then get is that the x becomes minus 2, square root of 2 over 2, and the y is square root of 2. So these are some more or less clever tricks to find those particular values. All of these, and this is something that is worth pointing out, all of these results will follow from trigonometric formulas. And we'll see these in a couple of minutes.